This is a tool call. By itself, it does nothing. It's one of 8 parts, and if you wire all 8 together the right way, a language model stops being a chatbot and starts finishing real work on your computer. Here's the strange part. The model, the thing everyone argues about, is only one of the 8. Some engineers put it at about 10% of what makes an agent actually work. So we're going to lay every part out on the bench, one by one, what it does, and how the agent fails without it. And at the end, we'll bolt them together and switch the whole thing on. Because none of these parts is the agent. The agent is what happens when they run in a loop. Let's start with the brain. Start with the part everyone knows, the model. Mechanically, a large language model is a next word predictor. Tokens go in, and it predicts what comes next, one token at a time. That's the whole interface. And 2 properties of that interface shape everything else in this video. First, the model is frozen. Training baked what it knows into billions of weights, and nothing that happens afterwards changes them. It doesn't learn on the job. Second, it's stateless. Every call starts blank. It has no idea what it said a minute ago, unless you show it again. So picture a brain in a jar. It can reason about anything you hold up to the glass. But it can't see your files. It can't touch your computer, and it won't remember you were here. Every remaining part of an agent exists to work around one of those 3 gaps. Which means the real question was never how smart the brain is. It's what you build around it. Part 2 is what the model actually sees, the context window. Every time an agent calls the model, it hands over one big block of text. The instructions, the conversation so far, tool results, pieces of your files, everything the model knows about this moment lives inside that block. Nothing else exists for it. Now, the window has a size limit. And 1,000,000 tokens sounds like more than anyone needs. It isn't. And worse, you don't really get the million. Inside the model, every token has to relate to every other token. 10 tokens make 45 pairs. 1,000 make about 500,000. Attention gets stretched thinner as the pile grows, and accuracy quietly sags long before you hit the limit. People call it context rot. Measured on recall tests, the best frontier model holds on to about 3/4 of a full window. Others drop below half. So the window isn't storage, it's a budget. And the craft people now call context engineering is spending that budget on the few tokens that matter and leaving everything else out. Part 3 gives the brain hands. Tools. A tool is just a function the model is allowed to call. You describe it inside the context. Here's one called run tests. Here's what it does, and here's what it needs. When the model wants it, it stops writing prose and writes a structured request instead. Run tests on the checkout module. The agent executes that for real and pastes the result back into the window. And here's the part that matters. The result comes back. The model reads the actual error, not its guess about the error, and that changes what it does next. That feedback is the difference between talking about work and doing work. One wrinkle you've probably heard of. MCP, the Model Context Protocol. It doesn't replace tool calling, it standardizes it. Before, every app wired up its own tools its own way. MCP is a common plug, so any assistant can discover and use any tool server, basically USB for tools. So now a frozen, stateless brain can fix a failing test. What it still can't do is know anything you didn't paste in. Part 4. Retrieval. Say your company's refund policy changed last month. The model's weights have never seen it, and pasting your entire wiki into the window would blow the budget from Part 2. So the agent looks things up instead, at the moment it needs them. The mechanism is tidier than it sounds. Every chunk of your documents gets turned into an embedding, a long list of numbers, and that list is a point in space. Text with similar meaning lands nearby. Your question becomes a point in the same space. So finding the answer stops being a hunt for matching words and becomes geometry. Measure the angle between the question and every chunk, take the closest few, and drop them into the window. That's cosine similarity. And that's most of the trick behind retrieval augmented generation. The model answers from your documents, instead of its memory of the internet. One caution before we move on. Retrieval is a lookup, not a memory. It can tell the agent what your documents say. It can't remember what you told it yesterday. That takes part 5. 4 parts from now, this all snaps together into one machine. But first, the agent has to stop forgetting you. Memory. And it turns out one kind isn't enough. A research team at Princeton mapped agent memory onto 4 types, the same way psychologists carve up yours. Working memory is the context window itself. What's in mind right now, fast, and gone when the session ends. Episodic memory is what happened. Last Tuesday, the deploy broke when it skipped the tests. Semantic memory is facts with the timestamps worn off. You prefer Python. The staging database is read only. And procedural memory is how to do things. Run the tests before every commit. Skill files, if you've met them, are exactly this. Written know-how, the agent pulls in when a job calls for it. But here's the clever bit. How does an agent keep all of that without drowning its tiny window? It borrows a 50-year-old trick from operating systems. Your computer pretends to have more memory than it does by paging data between fast RAM and slow disk. An agent does the same thing. The context window is the RAM. Files and databases are the disk. It writes notes out so they survive the session and pages the right memory back in when a task needs it. Same model, same window. It just stopped being an amnesiac. Part 6. Planning. Ask an agent for anything real, and no single tool call gets you there. Fix the bug actually means run the tests, read the failure, find the file, make the edit, run them again. Something has to break the goal into steps, and decide what happens when a step surprises you. The pattern most agents run is called REACT, short for reason plus act. The model thinks a step, acts, reads what actually happened, and thinks again. It's chain of thought with its hands touching the world, so the plan updates on real results instead of assumptions. And here's why planning isn't optional. Reliability multiplies. Suppose the agent gets each step right 95% of the time. Sounds fine. Chain 20 steps, and the whole run succeeds about a third of the time. That's not a bug in any one step. That's just what exponents do to long chains, which is why good agents plan short, check their work often, and never trust a long chain to luck. Checking its work, that's a part of its own, and it's next. 2 parts left before we assemble. This one is the agent checking its own work. After it makes that edit, does it just declare victory? The naive fix is asking the model to look over its own answer. And there's an uncomfortable finding here. On its own, that barely helps. A model that made an error tends to like the error on review. Same blind spot, second viewing. What actually works is checking against something outside the model. Run the tests and read the exit code. Take a screenshot and compare it to the design. Have a second model grade the answer against written rules. The signal has to come from the world, not from the model's opinion of itself. This, by the way, is why coding agents are ahead of every other kind. Code ships with a built-in truth machine. The test suite says pass or fail, and it doesn't care how confident anyone sounded. So reflection turns one-shot answers into drafts. Ground truth is what makes the second draft better than the first. Part 8. And then we assemble. The breaks. Everything so far makes the agent more capable, which is exactly why you want limits on it. An agent that can edit files can delete them. One that can call APIs can spend your money. So real agents run inside an envelope. Permissions decide what needs a human. Reading the repo? Sure, go ahead. Pushing to production? Ask first. Sandboxes contain the blast radius. Commands run inside a box, where the worst case is losing the box. Checkpoints. Snapshot the files before every edit, so anything reversible stays reversible. And tripwires kill the run. the moment a rule is crossed. None of this makes the agent smarter. It makes the agent safe to leave alone. And safe to leave alone is the property that decides whether you built a demo or a coworker. That's all 8 parts on the bench. Time to find out what actually makes them an agent. Because here's the thing, everything we just built is still a pile of parts. A brain, a window, hands, an open book, a notebook, a map, a checker, brakes, lay them on a bench, and nothing happens. What's missing is the machine that runs them. And that machine is called the harness. It's the part almost nobody talks about. And it's a loop short enough to say in one breath: gather context, take action, verify, repeat. Watch it run for real. You say, fix the failing checkout test. The harness gathers context, your instructions, its memory files, the tool list, all packed into one window. It calls the model. The model answers with a tool call. Run the tests. The harness executes it and pastes the failure back in. Around the loop again. Read the file. Again. Make the edit checkpoint first. Again. Rerun the tests. Green. Nothing left to do, so the loop stops. Every part you've met just fired. In order. On cue. And now, the claim from the start of this video. There's a coding benchmark called SWE Bench. Real bugs from real repositories. Take the same model, the exact same weights, and drop it into different harnesses. The scores move by 10 to 20 points. In one measured case, an open model scored 62% in its own harness, and under 4 in the wrong one. Same brain. The difference was everything around it. That's why the people who build these things keep repeating the same line. The model is the engine. The harness is the car. So when a new model feels like magic in one app and useless in another, you now know exactly where to look. So, every part of an AI agent. The model predicts. Context frames what it sees. Tools give it hands. Retrieval grounds it in your data. Memory carries lessons across sessions. Planning breaks big jobs into steps. Reflection checks the work against reality. Guardrails keep it safe to trust. And the harness runs all of them in a loop until the job is done. One honest caveat to take with you. That multiplication problem from part 6 never fully goes away. Agents still wobble on long jobs. And that's exactly why so much of the real engineering right now is happening in the harness, not the model. So the next time someone shows you an agent, don't ask which model it runs. Ask what's in the loop. Thanks for learning. See you in the next one.